Good day, folks. I'd like to take this time to talk about field interaction and details for energy systems. So let's get right to it, and at the end, I will show you a real working demo and foundation to start with. So this concept is based on the principle that energy can be extracted from the ambient field, not by conventional current draw, but by creating and manipulating voltage potential wells, high impedance discharge paths, and resonant magnetic structures. A capacitor is charged using inputs from open environmental sources, static electricity, RF harvesters, earth batteries, or similar ambient energy. This builds a high voltage potential well and electric pressure without drawing significant current. The key is not to collapse or discharge this pressure, but to use it as a stable reference to drive later stage interactions. The role of high impedance, high Z discharge. Instead of discharging the capacitor directly into a load, a high Z high impedance path is used, typically involving a fast switching device like an SCR, spark gap, or transistor to momentarily release pulses of energy. These pulses carry high voltage and minimal current and are used to stimulate a resonant transformer rather than to transfer power directly. This preserves the high potential state of the capacitor and prevents the destruction of the source pressure. The capacitor is acting as a gatekeeper, not as a current source. The air core high Q transformer as a resonant cavity. The system employs an air core transformer tuned to high Q resonance. In this configuration, high Q means the system has low energy loss and can sustain oscillations for extended periods. Air core removes ferromagnetic limitations and avoids saturation and hysteresis losses. The transformer behaves more like a radio frequency cavity, where energy resonates magnetically rather than being tightly coupled inductively. The transformer is not meant to work as a conventional magnetic flux transfer device. Instead, it operates as a magnetic field resonator excited by the high voltage pulses from the capacitor. Magnetic resonance enables nonlinear energy extraction. When the transformer is driven at its resonant frequency, it creates a coherent magnetic standing wave. The secondary coils are loosely coupled and tuned to the same resonant frequency. Instead of acting like conventional secondaries, they sip energy from the resonant magnetic field in much the same way a radio antenna draws energy from a broadcast. This is the key to Don Smith's magnetic resonance effect. Energy is not transferred from primary to secondary through conduction, but rather extracted from the resonant field, which is itself powered by brief high voltage pulses and maintained by ambient conditions. Utilizing voltage gradient across the load. Once the transformer is resonating, a voltage gradient can be established between its output and earth ground. The load is placed between this high artificial potential and the natural low earth potential. The resulting differential causes the vacuum or space-time medium to respond via displacement currents or field alignment effects. In this scenario, it is not the original capacitor or input source powering the load. Instead, the load is effectively acting as a channel between two voltage differentials, and the energy to sustain the current appears to originate from the field itself. The system taps into what would otherwise be seen as vacuum fluctuations or latent field energy. No direct energy transfer from the input. This approach fundamentally differs from conventional linear transformer systems. The input capacitor is not depleted by the load. The transformer does not transfer energy inductively in the traditional sense. The system behaves more like a high-frequency radio transmitter and receiver where energy coupling occurs through resonance and fields, not direct conduction. The load is powered by the field, not the input source. By combining a high voltage, low current capacitor, pressure well, high impedance pulse discharge, an air core high Q magnetic resonator, and a load positioned across a deliberate voltage gradient, it becomes possible to create a system where energy is extracted from the ambient field or vacuum rather than transferred in a closed-loop fashion from a primary source. This enables extremely efficient, nonlinear, and potentially over-unity energy interactions provided the system is properly tuned and the input pressure is maintained and not collapsed. Now let's move on to the less discussed parts of these types of energy systems. In traditional electronics, the term non-ideal transformer refers to a device that does not exhibit perfect linear energy transfer between primary and secondary coils. It may have weak coupling, higher leakage inductance, stray capacitance, or behave unpredictably at high frequencies. From the perspective of conventional circuit design, these are considered flaws. Because traditional systems demand tightly coupled, low-loss, highly predictable linear energy transfer, that's the paradigm of closed-loop, power-in, as power-out engineering. However, in field-based and resonance-driven energy systems, such as those inspired by Don Smith, Nikola Tesla, and Tom Bearden's work, a non-ideal transformer becomes a feature, not a flaw. Why? Non-ideal transformers act more like RF cavities than linear devices. When operating at high frequencies and in resonance, an air-core loosely coupled transformer starts to behave less like a power-conducting device and more like a resonant cavity or a radio antenna system. The magnetic field becomes detached from strict current flow and begins oscillating in space. The secondary windings interact with that oscillating field without loading the primary. This decoupled resonant interaction is nonlinear, enabling the possibility of field amplification and energy input from ambient or zero-point sources. So while traditional designers may call this non-ideal, it is exactly what is ideal for a system that aims to extract energy from the field rather than merely transform existing energy from one voltage or current level to another. Also to note, high impedance, high Z paths preserve the potential well. The use of a high Z, high impedance discharge path is crucial. High Z is essentially the electrical equivalent of extremely high resistance, which means that very little current can flow even at high voltage. This has two major benefits. It prevents the destruction or collapse of the input potential well, the charged capacitor. It allows brief, sharp spikes of high voltage, pure potential to exit without draining the source. Much like sipping from a pressurized tank using a needle valve. These voltage spikes, though low in actual current, can carry tremendous energy density when coupled to a resonant magnetic structure, such as an air core coil. That's because magnetic field intensity measured in watts per meter squared is a function of voltage and frequency, not just current. Also take note, it's from potential to magnetic, amplifying energy in the field domain. When pure high voltage potential is discharged into a resonant air core coil, the system transitions from an electrostatic domain into a magnetic field domain. Here's why this matters. The magnetic field doesn't care whether the driving force came from a conventional current loop. All that matters is the rate of change, that is, the voltage gradient over time. Even small high voltage pulses, when at resonance, can produce strong magnetic field oscillations with significant power density. At this point, the system behaves like a magnetic potential well, one that can store, amplify, and radiate field energy. The secondary coil, or even a nearby tuned antenna, can extract real watts of power from this field without collapsing the input capacitor. This is analogous to how a Tesla coil transmits energy wirelessly. It's not about transferring electrons, but about exciting and coupling to a standing field structure. The energy is not coming directly from the input source. It's being induced from the field by the interaction of potential and resonance. Also a very important point. The load must not collapse the source. It closes the field loop. In this configuration, the load is not powered through traditional transformer action. Instead, the input potential well charges a high voltage node. That node forms a gradient with earth or another low potential point. The load is placed between these two potentials. The resulting energy flow through the load closes the field loop, not the electrical loop. In this way, what appears as real current through the load emerges from the vacuum's response to the field conditions, not from a forced electron flow from the input capacitor. This is a kind of field displacement current where energy flows between 2 points of differing scalar potential enabled by high-frequency oscillation and vacuum polarization effects. Embracing non-ideal behavior unlocks new physics. This system works not in spite of being non-ideal, but because of it. Traditional electronics seeks control, predictability, and linearity. Field-based systems embrace resonance, nonlinearity, and environmental interaction. The so-called flaws in a non-ideal transformer become gateways to zero-point energy interactions, vacuum polarization effects, and field-based power extraction by mastering high-Z gating of pure potential using magnetic resonance in air core coils. Also consider voltage gradient field closure through loads. It becomes possible to design systems that harvest and amplify field energy rather than simply moving electrons in the loop. This is the bridge between conventional power and vacuum energy utilization, and it requires rethinking what ideal really means. Okay, folks, when we talk about crossing energy domains, it's important to understand this isn't limited to just the electric and magnetic fields. This concept applies broadly to all global energy domains, whether thermal, acoustic, mechanical, optical, or others. The key is to first identify what kind of energy output your system ultimately needs. If your goal is heat, consider how electrical or magnetic interactions might naturally produce thermal effects. If it's mechanical motion, look for field effects that convert easily into movement. If it's acoustic, consider how electrical pulses might induce vibrations. The goal is to leverage the environment's natural responses to initiate a trigger that causes a transition into the desired energy domain. Then let nature do the amplification for you in its native mode, rather than trying to brute force convert energy from one form to another inefficiently. Since we're primarily focused on electrical systems, we concentrate on the interplay between electric potential and magnetic fields. The idea is not simply to flip between the two, though that's part of it, but to set up a cascade of resonant domain transitions where energy is built up, not burned out. Each flip-flop event between electric and magnetic fields, when done in a high Q, high Z environment, actually adds field intensity. But here's the critical warning. Do not collapse the energy density during the cycle. This is where many experiments fail. When you introduce semiconductors, particularly standard diodes with PN junctions, they inherently try to clamp differences to ground. This instantly kills the field dynamics, collapses the magnetic dipole, and eliminates any accumulated gain. What should have measured as strong RF or reactive field power suddenly drops to milliamps and millivolts, even if you were just trying to charge a larger capacitor downstream. Preserve high Q and high Z. Through every stage, to maintain the field energy density, it's essential to keep the entire system, all loops, all transitions, and all resonance stages, and operating under high impedance, high Z, to avoid current drain, high quality factor, high Q, to maintain energy storage and minimize losses. Only at the final stage, where energy is meant to do real work, should the system interact with a load. That stage can then power your intended output, lamp, motor, converter, and on. Optionally, feedback into the input capacitor or storage bank to sustain or boost the system's input potential. Trying to close the loop too early, especially with a low Z path or traditional rectification, disrupts the entire cascade and stops the energy buildup process. In summary, crossing energy domains is about leveraging natural transitions to amplify and extract usable energy. This applies across all forms of energy, not just electromagnetic. In electrical systems, electric. Magnetic cycling must occur in a non-collapsing resonant manner. Avoid grounding elements or semiconductors that force a linear lossy collapse. Delay final energy capture until the last stage where the system has reached its maximum amplification. This is how nature handles energy, through resonance, balance, and gradient differentials, not brute force. Learn to work with it, not against it, and the gains can be surprising. Okay, folks, cascading nonlinear field events between coils. In systems that exploit high voltage, high impedance, and field interactive energy dynamics, the direct chaining of inductive elements such as coils is generally not feasible without collapsing the active dipoles involved. Attempting to connect one coil directly to another often results in the dissipation of the potential gradient, nullifying any attempt to retain or channel the accumulated field energy. To overcome this, energy transfer between stages must be performed via controlled, high-impedance gating, allowing for field transition rather than direct current conduction. Spark gaps, traditional, powerful, but challenging. In high-voltage Tesla-class systems, spark gaps have historically been employed to achieve this effect. Though considered primitive by modern standards, spark gaps possess complex and useful electrical behaviors, including negative resistance zones under specific breakdown conditions, rapid discharge triggering radiant event propagation through vacuum or low-pressure environments. However, engineering and maintaining the dynamic regime of a spark gap is non-trivial. The spark gap's performance depends on its operational zone, e.g., region A versus region B in Paschen-like curves, gas composition, electrode spacing, and field pre-bias conditions. These systems are nonlinear, stochastic, and sensitive to environmental conditions, making them difficult to stabilize or reproduce with precision. The limitation of standard semiconductors. Modern solid-state components, when used as is, generally do not exhibit the necessary field reactive behavior. Their functionality is typically dominated by charge carrier flow and linear response characteristics, which are insufficient for the kind of nonlinear potential-sensitive gating required in radiant or vacuum interactive systems. Closing a circuit loop with semiconductor switches alone results in dipole collapse, eliminating the very asymmetry required to maintain non-equilibrium energy conditions. Field-based gating, an alternative approach to bridge coils or field-active stages without collapsing the dipole. The solution lies in constructing a nonlinear field gate, a device that enables energy transfer through field interaction, not conduction. This is achievable by reconfiguring standard NPN transistors into field diode pumps. Transistor modification, turning an NPN into a field diode pump. A simple modification is sufficient. Short the base to the emitter. Configuring a bipolar junction transistor, BJT, with its base shorted to emitter does not simply replicate a diode's behavior. Instead, it introduces a nonlinear field-sensitive gate with temporal dynamics that significantly alter the system's response to radiant energy spikes. Nonlinear junction properties. This transistor configuration creates a junction with both capacitive and reactive characteristics. Unlike a conventional diode that immediately clamps voltage transients, this arrangement permits potential buildup prior to conduction. The result is a delay window during which field energy can accumulate, allowing for various forms of energy transfer or manipulation before the field collapses into conduction. This delay enables operations such as capacitor charging via displacement current triggering of secondary processes, whether optical, magnetic, or electronic, subtle biasing of the surrounding electret environment promoting stronger dipole field alignment. The behavior observed here differs markedly from a transistor in standard operation or with the floating base. The critical transformation arises from shorting the base to the emitter, which effectively suppresses conventional control pathways and reconfigures the device into a nonlinear field gate, a concept analogous to a field diode pump. In a standard NPN transistor, e.g. 2N22A, the base emitter junction behaves like a forward bias diode requiring A.6. The base current modulates collector-emitter conduction. The device acts as a current amplifier, not a field gate. Such behavior is conduction dominant, responsive primarily to charge carrier movement, not to field variations. By contrast, shorting the base to the emitter results in a distinct operational regime, collapse of the control layer. With the base directly connected to the emitter, the gate control mechanism is eliminated, no forward biasing can occur, and no base current flows. Formation of a nonlinear capacitive junction diode in this configuration. The collector receives high voltage radiant spikes. The base emitter is held at ground or reference potential. The transistor's collector-base junction becomes the primary active interface. With no base drive, it behaves as a nonlinear capacitor with dielectric properties that shift under field influence. This structure responds to voltage changes, dV/dt, rather than current flow. The result is a threshold-based field gate. We sip the field. Okay, folks, now let's talk in Tom Bearden's theoretical model of time-reverse phase replica waves. This posits the possibility of field-based self-correction and amplification analogous to concepts in nonlinear optics such as four-wave mixing and phase conjugation. In optical systems, the reverse phase replica wave can, under the right conditions, effectively correct an original distorted wave, improving coherence and energy transfer efficiency. When mapped into electrical systems, this would imply the potential for substantial energy gain, as the reflected phase conjugate wave acts upon the source system, reinforcing rather than depleting its dynamics. However, achieving this effect traditionally requires extremely precise frequency control, advanced materials, and the capacity to execute multi-wave interference patterns, typically outside the reach of most alternative energy researchers without access to high-end laboratory equipment. A primitive yet powerful approach, the self-oscillating Joule thief. Interestingly, certain primitive high-frequency self-oscillating systems exhibit behaviors analogous to time-reverse wave reflection, particularly when operated under free-running high-Q nonlinear conditions. One such system is a basic flyback-style Joule thief oscillator, a single transistor center-tapped feedback coil circuit. Despite its simplicity and noisy harmonic profile, this topology inherently satisfies many of the chaotic yet necessary conditions for spontaneous time-reversed wave replica formation: sharp nonlinear pulse dynamics, high harmonic generation, phase instability conducive to spontaneous phase conjugation. In essence, the chaotic nature of the waveform combined with reactive feedback randomly produces internal field alignments that mirror aspects of Bearden's time reversal model, albeit crudely and stochastically. The pitfall of closed-loop damping. When such circuits are closed-looped in a conventional manner, for example by connecting the oscillator directly to a load, such as an LED, the result is a destruction of the time reversal effect. The direct connection completes a conduction path that collapses the vacuum dipole asymmetry, dissipating the radiant or displacement-driven energy before it can reinforce the system. This explains why such effects go unnoticed in typical implementations. The phase-reversed regenerative condition requires a system that can recycle potential without collapsing the dipole, a non-trivial requirement in traditional electrical engineering, but essential in scalar or field-coherent models. The additional modified transistor in this oscillator configuration behaves not only as a switch but also as a phase-locking feedback element. Under exotic pulsed and resonant conditions, it may serve as a quasi-field diode, creating feedback pathways that allow time-reversed energy signatures to couple back into the system. To exploit this effect properly, careful design of the gating components is essential. It is not sufficient to adjust resistors or reactive elements arbitrarily. Instead, the system must include a nonlinear field interactive gate, a device that automatically adjusts based on system dynamics and field conditions. One effective implementation involves the modified NPN transistor configuration with base shorted to emitter, acting as a nonlinear capacitive field gate as described earlier. When configured correctly, these circuits exhibit anomalous behavior that suggests a reversal of conventional current flow. Specifically, load current appears to flow against the expected direction. The energy source, example a depleted or dead cell, seems to possess excess power not accounted for by chemical or stored charge. Placement of an LED in the feedback return path to the power source can reveal backflow current, indicative of displacement current or vacuum-induced gain. This behavior aligns with the concept of time-reverse phase correction, where the system draws energy not merely from the power source but from its field environment, potentially via zero-point energy (ZPE), coupling or local vacuum regouging. Okay, folks, while the described system is not a turnkey device, it serves as a teaching and prototyping platform. It allows for observation of field-based energy interactions, exploration of phase-conjugate electrical behavior, development of alternative gating, and feedback strategies for enhanced gain. Importantly, the system should be viewed as a conceptual foundation, not a finished product. Users are encouraged to customize the component values based on available parts, observe and measure harmonic behavior and load feedback, refine the gating topology for more consistent reverse phase coupling. By embracing the chaotic, nonlinear nature of crude oscillator circuits and combining them with carefully placed nonlinear gates, it is possible to replicate conditions approximating Bearden's time reverse replica wave theory. This creates a gateway for alternative energy exploration without the need for exotic laboratory conditions. Future iterations may incorporate improved transistor geometries for sharper gating thresholds, parallel coupled resonant cavities for enhanced harmonic feedback, optical or magnetoelectric triggering for field-aligned switching. This direction represents a practical entry point into scalar and field-based energy experimentation. A schematic overview will follow to illustrate the basic layout for experimentation. It is recommended that experimenters fully understand each conceptual section before assembling the circuit, as improper configuration can suppress or entirely nullify the time-reversed wave behavior. Tom Bearden proposed that every electromagnetic EM signal inherently contains two components: time-forward EM wave, the observable wave in classical electrodynamics associated with conventional current and voltage flow; time-reverse replica wave, the hidden counterpart moving in the opposite temporal direction, typically cancelled out or averaged. In most conventional systems, these two wave components interfere destructively or become functionally invisible due to symmetric energy dissipation and dipole collapse. The dipole returns to equilibrium, and no net energy gain occurs. Preventing time wave cancellation in nonlinear high-impedance systems. In the system under investigation, wave cancellation is partially or entirely prevented by a combination of design factors: minimized resistive current flow through use of high-impedance, high-Z elements; introduction of time-skewed reactive components such as reverse-biased electret materials; nonlinear junction gating with delayed response, example base emitter shorted transistors; radiant pulse feedback directed into the dipole source rather than into a dissipative load. This configuration establishes a scalar potential gradient, an asymmetry in the field structure which becomes a medium for interaction between the time-forward wave and its time-reversed replica. When the TRW interacts with the preserved dipole, the resulting field dynamics enable apparent amplification from the vacuum domain rather than through conventional energy supply mechanisms. Apparent reverse current, a consequence of time-space. Field reconfiguration. The observed phenomenon of reverse current flow is a manifestation of altered field geometry. In classical circuits, current follows the voltage gradient across a resistive path. In this case, the voltage gradient that exists between two high-impedance potentials, with EMF established by inverted time feedback, not conventional potential difference. This creates an energetic scenario analogous to inverting a gravitational potential. Objects appear to fall upward not because gravity is reversed, but because the field structure has been inverted across a local space-time curvature. The system does not recognize this inversion as abnormal. As such, current appears to flow backwards, not by violating conservation laws, but by reorienting the path of least action through a regauged vacuum environment. Conditions that enable apparent gain. The system is not creating energy in the traditional sense. Instead, it allows vacuum energy to enter the circuit through an asymmetrical regauging event. This is key to Bearden's model of energy amplification without current draw. Gain appears when radiant feedback is injected into the dipole source but does not collapse it. The dipole is conditioned to respond to the time-reverse replica wave. A transient window of vacuum interaction opens, turning the dipole into a gate for ambient potential. That external potential expresses across the load, producing measurable current without corresponding power input. This process exemplifies Bearden's assertion that conditioning the system is more critical than powering it. Once correctly conditioned, the system self-aligns with external energy flow. Experimental alignment with Bearden and Floyd's suite. The observed experimental behavior closely matches previously reported outcomes by Tom Bearden and Floyd Sweet. Latency between radiant excitation and load response, current detection across high impedance loads without conventional conduction, feedback-induced amplification events, system behavior dependent on bias polarity or field orientation. These results support several scalar and nonlinear field theories, including time-reversed wave, TRW, interference, scalar potential gradient manipulation, vacuum curvature interaction, confirmation of time-reverse feedback loop activation, where one does not force energy into a system but rather alters the surrounding conditions such that ambient potential falls in. Through careful high-impedance gating, delayed conduction timing, and scalar-aligned feedback, the circuit achieves conditions under which time-forward and time-reverse wave asymmetry can be maintained. This permits vacuum regauging, non-local potential interaction, and energy domain transduction, resulting in measurable system gain without conventional energy supply. Don't power the system, condition the system to be powered. Okay, folks, I will try to explain this circuit in a nutshell. It is a starting point. Feel free to experiment with it. So to start, let's look at the DC power input in series. The three devices in series, electret A, the bench supply, and electret B, form a closed DC loop that barely moves any charge. Both electrets behave like 1-volt capacitors with sky-high resistance, so the loop is complete on paper yet practically current-starved in reality. That starvation is important because almost no line current flows. The bench supply's dipole never collapses, leaving a standing electric field in the wire that can be nudged without being drained. Electret B is wired in reverse polarity. In a chemical battery string, that reversal would spell heat and damage, but an electret is nearly lossless. When biased backward, it simply stores the stress as electric field rather than turning it into heat. The result is a high Z element that looks broken by ordinary standards yet remains perfectly calm, holding its inverted charge like a tightly wound spring. From the supply rail, a small NPN transistor and transformer T1 sip only milliamps while switching tens of thousands of times per second. The 60 Hz iron core in T1 cannot follow such speed gracefully. Each switch off sprays flux in a ragged burst. That burst, rich in voltage but lean in current, is the outgoing signal wave in Bearden's terminology. The burst charges the collector base capacitance of a second transistor whose base is shorted to its emitter. With the control junction disabled, this device stops acting like a current valve and starts behaving like a silicon trampoline. Voltage stretches the junction silently to roughly 900 V, at which point the stored field energy avalanches through in a nanosecond snap. Because almost no charge from the supply crossed the junction while it was stretching, the snap is powered almost entirely by field tension, free to carry a phase-inverted time-reverse signature. Transformer T2 catches that snap and rings for a few microseconds, smoothing the raw spike into a compact pulse. A fast diode in series makes the path one-way, guaranteeing that none of the pulse energy can leak backward and short out the carefully preserved dipole at T1. The shape pulse lands first on the reverse side of electret B. For that brief moment, the pulse's polarity aligns with B's natural orientation, so the electret lowers its impedance and absorbs the incoming field without fighting it. The stress then emerges on B's other plate as a real measurable current that pours straight through whatever load is connected across B. Ordinary multimeters show tens of milliamps. Impossible for a 1-volt electret in steady state. Yet the bench supply still registers only the oscillator's few milliamps. The extra energy is coming from the transient realignment of the electret's internal field, not from the DC source. Electret A on the far side of the supply remains essentially silent. Because the chain stays high impedance and the diode blocks any backward surge, A never sees a strong enough pulse to conduct. It therefore never shunts the dipole and the standing field in the red wire remains intact. Switch off the bench supply and the whole tableau collapses in an instant. The oscillator stops, the silicon trampoline is no longer stretched, electret B flips back to its original reversed bias, and the load current falls to microamps. No lingering power, no hidden battery, no hot parts. Proof that the surplus current existed only while the phase conjugate echo was being generated in real time. In short, a reversed high-impedance electret does not waste energy as heat. It stores field stress. A flyback pulse that is mostly voltage stretches a nonlinear junction. The junction snaps back with a time-reversed burst, and that burst momentarily turns the wrong-way electret into a doorway through which field energy pays the load while the bench supply remains almost untouched. That is the essence of the phase conjugate mirror idea rendered in wires, silicon, and $2 store transformers. Simple parts lined up so that the vacuum itself supplies the drama.
Alright, so to start, here is my series electrets. So this would be in the schematic cell A, and this would be our cell B over here. And my power supply, as you see here, it's really messy, the wires, but this is my input for the power supply here, which I have set to 10.9 volts. It's off, so without the input in the middle of the circuit, I've got the scope on there on this side here, which you're not going to see much because we don't have enough voltage to start the oscillator, but I could measure this B cell is about 1 volt, okay? So I got the meter on there right now. And what's going to happen is when we turn this on, because of the non-ideal cell, it's going to want to flip polarity, like acting like a really bad cell that can't even provide enough current to make it through the loop. Then it gets reverse bias, right? A normal cell that's really bad because it would just act as a load instead of a contributor and suck up and basically as a low impedance load. But because this is also a capacitor, what it does instead is it flips the polarity, yes, but then it captures it as a field and then does like a capacitor, acts passively like it doesn't do anything. But because it's high Z, it still then lets like a passive bypass essentially. So it no longer loads it, but you got that reverse, but it doesn't really do anything. So if you want to take advantage of that in the circuit, you make it non-ideal. You flip the polarity so it goes from input negative to negative. So when you run it in the series, then it will inadvertently flip to its natural polarity and then contribute, and all of a sudden you got an amplification and the oscillator gets the potential in the chain as it wants. So here's the little oscillator here, and this is the first transformer, center tap. Go into our modified transistor here, then the output of that goes back into the input of our cell here, and down here I have my load, which is directly connected to the cell B here. By the way, this is like maybe less than 0.5 mA if lucky, so directly feeding off of this, especially that there's there's a high Z on each side of it. Being connected to here doesn't directly allow me full access to the power supply, so that's why it doesn't drain it either. So I am going to show you this. Just going to put this back on so you can see the voltage here, pure potential. So now what happens is when I turn on the power supply over here, I basically start the transistor, so it then completes the high Z loop, and we get to see how much current we're using. It bogs down, it starts for a while, then goes down to about 33 mA, 32, 33, which is very good, and there's our pulse there. And I could hear it very strongly in the transformer here. And look what's happening over here now. So what you can do now is, like over here I've got my load, so I can run a motor, no problem. I could even burn parts off of this, and basically I don't have enough power just from the power supply, but the field dynamics is allowing this to happen. Now if I want to know like essentially how good I'm doing, I can go bring this to 10 ohms and I can measure the voltage here. Take a moment and see when it stabilizes the drop. Then you can measure that and figure out what your power is versus your input. So we got the oscillator running here. We're going to give it a moment to stabilize because we're loading it. We're really loading it at 10 ohms. You know, it's still running strong. Just waiting for it to plateau here. But this is being loaded, by the way. And it takes about a minute. And you can do the math against what you're putting in yourself. And this tells you what the load is, so you can't really cheat. You know what you're putting in. And through the load here, because we have it direct, so cell B is right into the 10 ohm load. So you look at your voltage and you can figure out just an example, right? So this is essentially it, and you'd be surprised to find out that you've got gains here. I've measured anywhere, it varies a little bit. As you see, this is a very crude setup in the environment, you know, humidity and all that, and if it's dry and whatnot. Electrostatics like really dry weather, right? So mileage will vary, obviously, but I have had anywhere from 10 to like 40 milliwatts of extra that was on top of what I was providing here. So, but as you see, look, we're loading it, and it hardly went up. It started at like 33, right? And we brought it up to like 37 by loading it down with that 10 ohm. And we're doing good. It's stabilized now to 0.526 of a volt. So 0.526 of a volt at 10 ohms, you can figure out against your input here. This actually gets more efficient with time, by the way. So it goes down to like, it's going down to 36 mA on the input and stabilizing out here. So this is why, you know, instead of the load now, this is just artificial, we're wasting it. Let's go back to motor here. You can see the motor runs super fast directly off the cell B through the reverse wave, the correction, Tom Bearden stuff here. And to show you that, look, we're going to kill the oscillator here, and it's going to kill all the effects. So I'm going to switch the voltage off. And look what happens. It takes a moment because it's like a capacitor, right? I turned it off. But then finally, because it wants to feed itself back for a while, right? Because it's such an efficient system. So without the trend, as you see, we're off. We don't have enough forward current in our loop. These on their own will not power right now this transistor. But with the aid of the in the middle series DC through the high Z loop, I'll turn it back on here. There you go, it's instant. And it basically doesn't feel itself from the input, and you get that additional. So now whatever the impedance of this motor is, we're staying stable at 1.367. But that's essentially how you figure it out. Very simple but obvious way, right? So this is it. As represented, and again, you know, your field diode, you're flipping the domains. And what's really interesting here is after I did this, I was getting, without feedbacking it, I was getting like almost 900 volts pulses. And when I had no regular diode there, I was lucky to get 14. And when I tried to do anything with it, it went down to like half or nothing. And this isolated all nicely. And there's that feedback effect. So what happens, the extra here from the cell is like getting reverse modulated by the transistor, and that's how it reinforces, because what happens is we can kill that reinforcement. I'm going to show you that. I'm going to turn the motor off here. I'm going to show you the voltage. So this is the motor's off, so it's going to climb a little here. And what happens is I've got the feedback here. So once I disconnect, so I'm going to find the feedback wire. I'm going to disconnect the feedback wire. See how it jumps when I put it back? Oh, you didn't see that, but there's the feedback wire. It just goes a lot, I don't know if you can see that, but it jumps a lot faster when I turn it off because it completes the DC loop, but then with the aided, this helps it. This makes it makes the climb a lot faster. Another way of doing this is you could put a load in between the feedback, and you'll see it. This is where I noticed with an LED the current was flowing from the cell into the transformer as a closed DC loop and being modulated by this, and you know, kind of like a reverse magnetic amplifier of sorts. So this keeps amplifying because it's being reverse biased in its right direction and then contributing back in the right polarity. So we started off hooking it up in reverse, but because it's a non-ideal loop and the high Z natures, it feels like a really, really bad cell, but then it acts like a capacitor as soon as it gets charged and then passively hovers along here. So this is where the current comes from. Motor. There you go. With very minimal strain on the input load, it basically doesn't feel it. And everything keeps running here and it's doing its thing. But of course, as soon as we turn it off, over here, I'm gonna turn it off. See 25 mA there, that was pretty good. It still spins for a while. See, I turned it off there. And it's still going. That's kind of remarkable, actually. This is new. This is quite a long, because I turned it off, you see that? That's amazing. It's slowing down, but this is really, it's keeping itself going. You know, like I said, gets more efficient with time. This is amazing, because I've got it off, folks. Oh, it's gonna drop out there. Hey, that was a long run, huh? Oh my goodness, it's still feeding itself. Wow, okay, now the oscillator stopped. See how long that feedback went for? That's a record right there for me. Sorry, I'm all excited because I caught it live on the camera. Usually when I turn the power supply off, the effect wears out right away. But this sustained it, you know, my goodness. Quite a lot of capacitance in these electrodes, let me tell you. With that said, I hope you enjoy. Again, quite complicated, but this opens the door for, you know, introductionary experimentation and understanding the Tom Bearden concept and what we've been doing. And of course, I'm sure this will work with the PEG cells that we've been doing for a couple of years now. This is the sodium metasilicate. I've had earlier videos demonstrating some similar things, but I'm just trying to wrap it all up into a perspective that most people can understand. I know this looks ugly here on the bench, right? But that's why I made the schematic, so you can kind of follow along here. With that said, again, it's nothing specifically new, just maybe trying to reward everything. And of course, this is not going to power your house, right? But it's to show you that you could experiment with all of these effects that Bedini, Don Smith, and everyone else, and Tom Bearden, without all the fancy stuff, just around, okay, oh fine, it's not ideal, but it'll open the door to understanding or new mechanisms of gain and whatnot. And this is the kind of thing that'll get you thinking and potentially building better systems, if that's what you're into, right? And of course, phasing into more like the Don Smith. See, we're not even really including any major tuning resonance or anything like that. We're using recycled parts. Can you imagine, you know, flipping the domains with resonance and all of that stuff, right? But needless to say, it's nonlinear. High Z, keep the dipole open, use that field gate mix of electrodes and modify it. Everyone had that element. You know, Bedini was the doped semiconductors, Floyd it was the barium, Bedini, you know, they all have. Don Smith too had his unspecified, you know, modified resistors, and that's the thing. Everyone has this thing to make it a field gate and not a electron flow to keep the dipole open. And as long as you interface that, because it's more than just, you know, crossing domains, right? I mean, you can keep flipping it with a transformer, but if you don't know what you're doing and you keep everything linear, you're not going to get anywhere with that. And to confirm you can have the magnetic meter here, and what's nice is when this all runs, the field stays very strong, which is another indication that if you were siphoning the magnetic field, I wouldn't be able to get a reading. But here I get a super strong reading. See, it's set to the magnetic field. So I'm getting nothing now. I'm going to turn it on real quick because I want to show you that. I forgot to show you. And look at it. It starts acting more like an RF, like a Don Smith even, because it's high frequency. But look at that high field. It's pretty strong, right? Because we're bringing it into another domain. We're letting nature amplify it in its own domain. And the field density is very strong, and that's what we're sipping into, without killing the dipole and amplifying it on each side. You know, because if you stick with field dynamics and you keep flipping the domains, you essentially bypass traditional ohmic losses in every stage. And that's part of it. So I hope I did a good job trying to explain it all. And until next time, folks, and have yourselves all a great day. And looking forward to hear your experiments with your peg cells. And I've been working on these cells now, you know, for 2 years or so, and trying to find a good application for them. Maybe this is it. To introduction on Tom Bearden's time reverse waves and how to utilize them. So several mechanisms all working together here to get this effect. It's not specifically just the oscillator, just this transformer. It's a singing orchestra, essentially, of all the interactions we can possibly do here on my bench.
In the world of science, progress often involves updating frameworks when data demands it. A clear example lies in the field of aerodynamics. For decades, simplified models couldn't explain how bumblebees could fly. Once this discrepancy became undeniable, scientists revised their models by introducing external environmental factors such as air turbulence, vortex shedding, and dynamic wing movement. This was celebrated as scientific progress, a rational adjustment to better fit observed reality. However, a curious inconsistency emerges when the same logic is applied to electrical and electromagnetic systems, particularly those that hint at interactions with subtle external energy sources, such as quantum vacuum fluctuations or ambient field effects. Proponents of these advanced ideas find that instead of open-minded curiosity, the scientific establishment often meets them with rigid resistance. The crux of the matter: closed versus open systems. At the heart of this divide lies a fundamental conceptual misunderstanding. Traditional science treats electrical circuits as closed systems. Energy is thought to flow only from clearly defined input sources, a battery, a generator, or a power supply, with losses and outputs tightly governed by established equations and efficiencies. When researchers present either experimental or theoretical results suggesting that these systems might tap into external or environmental energy reservoirs, producing more energy output than classical models predict, mainstream scientists are quick to dismiss such findings as measurement errors or pseudoscience. Yet, this is not because these results inherently violate physical laws. Rather, they challenge the entrenched boundaries around those laws, boundaries that are often culturally and historically imposed, not scientifically required. The aerodynamics analogy, a tale of two standards. The difference in treatment becomes glaring when we revisit the bee flight example. When classical models failed to account for bee flight, scientists didn't dismiss the phenomenon. They expanded the model boundaries to include previously neglected environmental inputs like unsteady airflow and vortices. They reclassified B-flight as an open aerodynamic system, and in doing so resolved the contradiction. So why is the same flexibility not granted in electromagnetic systems? Three key reasons behind scientific resistance, dogmatic boundaries, and physics frameworks. Traditional disciplines like thermodynamics and classical electromagnetism are built upon strictly bounded models. These models define energy systems as closed loops, where all energy sources and sinks are explicitly defined. Introducing concepts such as scalar potentials, vacuum energy, or ambient field gradients threatens the ideological architecture of these systems, not the physics per se, but the interpretative boundaries handed down through textbooks and institutional education. Dismissal of subtle energy sources. Mainstream scientists often ignore or trivialize energy sources that are subtle, difficult to measure, or not well understood. Examples include zero-point vacuum fluctuations, Earth's electrostatic potential gradients, environmental scalar fields, resonant electromagnetic coupling. Ironically, these are precisely the kinds of inputs that aerodynamics accepted to explain B-flight. Once subtle vortices and air turbulence were acknowledged as real contributors, the model was validated. A similar shift in perspective is all that's required in electromagnetics. And three, institutional and sociological constraints. The resistance isn't purely scientific. There is a sociological layer to this problem. In fluid dynamics, adding external inputs doesn't challenge political or industrial power structures. But in energy systems, the implications are transformative and disruptive. Acknowledging the possibility of tapping vacuum energy or ambient fields undermines major economic and scientific paradigms. Throughout history, figures like Nikola Tesla, T. Townsend Brown, John Bedini, and Thomas More faced harsh opposition for suggesting similar ideas. Their work wasn't rejected purely on technical grounds, it was actively marginalized because it disrupted established models and economic structures. Despite this resistance, there are constructive ways forward for those interested in pushing these boundaries. 1. Redefine electrical systems as open systems. Start by explicitly proposing that electrical systems are inherently open, capable of interacting with external energy fields, including the quantum vacuum, gravitational gradients, and ambient electromagnetic flux. Just as aerodynamics expanded its scope, electrical engineering must do the same. 2. Measure the unmeasurable. Encourage and develop measurement tools and methodologies aimed at detecting subtle inputs. Some possibilities include monitoring Earth's ambient electrostatic field changes, detecting scalar potential gradients in atmospheric or near vacuum conditions, studying resonance coupling in specific magnetic configurations, observing energy anomalies in high voltage or high frequency circuits. Once measurable, these phenomena will become increasingly difficult to dismiss. 3. Use analogies to reduce psychological resistance. Draw parallels between accepted open systems like solar panels, sailboats, heat pumps, or biosystems, and speculative energy systems. Showing how accepted devices depend on external energetic inputs makes it easier for skeptics to see new technologies as extensions, not violations, of known science. 4. Focus on repeatable instrumented experiments. Build carefully controlled experiments designed specifically to detect and quantify external energetic influences. Emphasize replicability, precision, and transparency. Over time, well-documented anomalies force re-examination of outdated models. Final thoughts and encouragement. This isn't about abandoning science, it's about expanding it. The double standard in scientific openness is not a flaw in logic, but a product of historical momentum and institutional conservatism. And while frustrating, it is also the precise boundary where innovation occurs. Those who recognize these inconsistencies and ask deeper questions are not wrong. They are often the pioneers of the next scientific paradigm.